paper that I need to get into your hands is the class notes, are the class notes for today. And then, guys, we're going to circle the wagons and have a big old conversation. Stuart, how are you?
Good.
Yeah? Silas, would you hand those down? Well, Cade, here we are. You know what, though? Tomorrow's Saturday. I know. I think it's starting to... I'm sensing that sort of universally. Or maybe it's just because I am. All right, guys. So... What I'd like to do is begin a conversation that we will never have again. Guys, we are going to settle in, we're going to spend the next 20 minutes talking about your tests. Guys, I believe I alluded to this when you took the test, but you probably understand that Miss Call and I don't do things like any other teacher at Orem High. It doesn't mean these aren't good teachers, but it means Miss Call and I are deeply and personally invested in your success. And other teachers could be too, they're just not as good at organizing it. So guys, what I'm about to share with you, whether you know it or not, is an amazing opportunity. So much so that Wednesday night at parent-teacher conferences, as I was sitting down with many of your parents, as I explained to them what I'm about to explain to you, you could see their faces kind of go. And their response was, seriously? You do that for your students? And I went, oh yeah. Guys, we are going to spend the time necessary to help you understand how we deal with tests. But we will never do this again. We will do this again, but we'll never talk about it again. When you get your second test back, guys, we don't even need to talk. And you guys are just going to start, and you're going to do everything we're about to do all on your own. Because I'm going to teach you how to do it now. So guys, this is the way it goes. Slowly, this is the way it goes when you get tests back. Guys, the vast majority of the tests that you take free response section. And when they do, I will show you the key. Flip your tests over. This is the key to the back of the test. Join me. The first part where you were writing a procedure was worth 4 points because there were 4 steps. You could have chunked them together differently, but all 4 had to be there. Step number 1 had to be step number 1. Weigh the cylinder. It's got to be empty. Then, guys, step number 2 is not implied. You have to say, add the liquid. You can't say, weigh the cylinder, step 2, weigh the cylinder plus the liquid, because there ain't any liquid in it, because you didn't say add the liquid. That's not implied. So, step number 3 then, guys, and 3 and 4 could be in either order. You needed to weigh it with the liquid and read the volume. The order doesn't matter, but all 4 things had to be there. You good? Okay. Then, guys, the next part of the lab was your data chart. This was worth 6 points. Notice your scores are to the left. Guys, these are the things I was looking for. 3 points for units, grams, milliliters, and grams. And then 3 points for the right number of decimal places, 2 and 1 and 2. 2 in the masses, because that's what our balances do, and 1 for the volume, because we estimate to tenths with our graduated cylinders. Then, guys, the next thing you had was a calculation. It was a mass by difference calculation. Remember, structure and organization matters. Mass of cylinder plus liquid minus the mass of the cylinder gives you the mass of the liquid. Organized well and first. Then you set up your subtraction. The number, the pound signs, the hashtags represent numbers. Notice, guys, that these are your masses, so they add 2 decimal places, which means you need 2 decimal places in your answer. And if you did the subtraction and it was like 4 minus 4 is 0, you got to put the 0 because it's significant. And that's that worth 5. Then, guys, you have a density calculation where density is equal to mass divided by volume. Most of your masses had 4 decimal places. Most of your volumes had 3 decimal places. Therefore, you get 3 decimal places in your answer and units on the numbers. Then, guys, finally this, and this is where, if mistakes were made, this was common. Guys, at the very bottom of this, you're doing your percent error calculation. And this is the mistake you made. So you write down the equation first, and then you plug in your numbers. But guys, for most of you, you add 2 decimal places in your calculated density. There were 2 decimal places in the given density. So when you did that subtraction, you should have had 2 decimal places in the difference, right? But for many of you, the first decimal place was a 0, and the second decimal place was a number. When you then do this division, that means you only get 1 significant digit in your answer. For most of you, that was the case. Now, guys, if you missed any points on that, look at multiple choice question number 54. Flip your test over. If you missed any points on that, you probably also got number 54 wrong, because, guys, number 54 was the same idea. How many significant digits in that percent error calculation? And the answer was 2, because the subtraction gave you 2 decimal places. So, guys, any questions about any of this? Okay, then, oh, go ahead, Julie. No? You okay? And then dividing is?
You always look for the decimals, like, sorry.
Yeah.
Like you do the lowest, so I was mine.
Yep.
Like 1 left, 1.12 minus 1.1.
Mm-hmm.
It would be
1 decimal place. Yeah, you got it. Yep.
Mm-hmm.
Exactly. Yes. Yep. So, guys, there's one other thing I would like to talk with you about. In the multiple choice, there's an unfair question. I don't remember the number. It's the question that talks about precision of a balance. 27. So, guys, on question number 27, that is an unfair question. This year in class, let me tell you the answer. Guys, precision means repeatability. So in order to verify that a balance is precise, what you need to do is weigh the same object several times. But guys, frankly, that just got past the editing process for Miss Call and I. So guys, what we're going to do is I am going to give all of you another point on the test. So when I put these points in skyward, there's a magic button that I can click that says add a point to everybody's score, and I'm going to do that. So I don't care if you got it right or wrong. It wasn't a fair question. And rather than have to figure out who that hurt or not, I'm just going to help you all and give you all an extra point on the test. Okay? So that's how we're going to handle that. You guys good? All right. So guys, this is where your parents thought I might walk on water. Guys, check this out. You're going to have the opportunity to do this guys, for the rest of the year. So here's the deal. You guys know everybody in the school is sick, right? Everybody's got this thing that starts with a sore throat and then the next day it goes into your chest and it lasts for a month. Yeah. You know why everybody's got this? It's because of you guys. because you guys are the students that won't let yourself stay home. You would rather like die than miss school, right? So guys, why? What happens when you miss school? Why is it better to come to school sick than miss? I've got kids tell me this all the time. Mr. Knappenberger, your class is the only one I came today, but I came to your class because I didn't want to miss anything. What are you worried about? What happens if you miss something? You're lost, right? If you miss something, you come in the next day and you have no idea what we're talking about because you missed it, and then you missed that day, and it just balloons and balloons and balloons, right? Guys, here's the problem. For some of you, those issues aren't small, they're bigger. And guys, for some of you right now, you took this test and you're like, oh my gosh, I didn't do so well on this test. And guys, the problem is not the score on the test. The problem is what if there's stuff on the test that you don't know, and that is going to cripple you for the rest of your time in this class? Wouldn't it be nice to know what those things are so that you can fix it? And wouldn't it be nice to get points back for fixing those things? Well, guys, that's what we do in here. Every time you take a test in this class, I am going to tell you, and guys, join me at the board, I am going to tell you what are the essentials. So guys, what are essentials? Essentials are the things that you have to know. If you know them, you can breathe a sigh of relief and know that you can move forward because you know what you know and you know what you need to know. But guys, if you don't know the essentials, you're not left guessing. You can go, all right, this is the thing I don't know, and as soon as I learn that, I can move forward with confidence because I'm good. Don't you wish you could say that in all of your classes? Don't you wish you could say with confidence, I learned what I needed to learn in that last unit regardless of my test score and I can move forward, or I might not know this, but he told me what I don't know and I can fix it? That's what we do in this class. So guys, we call those things essentials. But if some things are essentials, some things are non-essential. We call those things fluff. They're fun to know and they're nice to know, but you could spend the rest of your life not knowing those things and be okay. And guys, in order to figure out where you're at, you need to know which is which. And we're going to talk about that in a minute. But guys, once we understand what the essentials are, this is the conversation that we need to have. Look at your test score. Flip to the front of your test and look at your score. Guys, your test score falls somewhere on this line. So let's talk about where you might be. So guys, what if your test score is between 85 and 100%? That feels pretty good, doesn't it? But guys, here's the thing. You might still be in trouble. There's the possibility that you got a 95% on this test, but you still don't know one of the essentials that you need to know to move forward. I don't mean to be a wet blanket, but guys, if you did really well on this test, it doesn't mean you're ready to move forward. You're going to know in a minute if you are. So guys, what about this? What if you're in no man's land? What if you're somewhere between 75 and 85? Not bad, not great. What does that mean? Well, guys, we don't call this no man's land. This is extra credit land. Guys, if you are in that range of test scores, here's what we're going to do. We're going to help you figure out whether you know the essentials. And if you are in this range of scores, and if you know all the essentials, guys, you learned everything you needed to learn. The reason your test score is a little bit low is because you didn't learn the fluffy stuff. So guys, if you are in this range of scores, but you got all the essentials, I'm going to give you extra credit to reward you for knowing the essentials. You don't have to do anything. I'm just going to give you extra credit. Now, Guys, what if you're down here in this land? That's sort of the danger zone. Now, guys, what if you're down there in the danger zone, but you know all of the essentials? Congratulations. That's awesome. Because you know all of the essentials, and the stuff that you don't know is you just didn't know a lot of the fluffy stuff. Here's what I'm going to do. Guys, you could get a 2% on the test. None of you did. But you could get a 2% on the test, and if you know all the essentials, I'm going to raise your test score all the way to a 75. Here's what I'm thinking. If you know the essentials, that's worth a 75% regardless of anything else you did on the test. And I will raise your test score right now to a 75% no matter what you got. Okay? But now, guys, what about this? What if you don't know all of the essentials? Well, guys, if you're in this zone and you don't know all the essentials, it was probably just a stupid mistake. Some of you are having that experience right now. You're like, oh man, I can't believe I did that. You're okay. But if you're in this zone and you don't know, or I said that wrong, it's not the non-essentials, it's what if you don't know some of the essentials. So guys, if you don't know some of the essentials and you got a high test score and you're still confused, come and talk with me. I'll help you. But guys, what if you're here, or what if you're here, and what if you don't know some of the essentials? And guys, the answer to that question is remediation. Guys, you are going to remediate. You're going to learn all of this material, the essentials that you didn't know. And when you do that, I will give you extra credit, or I'll raise your test score to 75. So guys, the bottom line is this. If you remediate, the lowest your test score can be is a 75. And if all the rest of your work in this class is solid, that's a B. So guys, the lowest score that you can get, the lowest grade that you can get in this class, so long as you're doing the remediation and so long as you're turning in everything on time and well done, the lowest score you can get in this class is a B. That's it. So, guys, how does this work? Let me show you. Grab that other sheet of paper that I gave you. The one that looks like this. Guys, grab this dude. So guys, this is it. Put your name on it. You can just set them there. Guys, put your name on this piece of paper and then put B3, because I don't understand what B7 means. And then guys, watch. You're going to turn this paper into me. So do this with me. Guys, here it is. No secrets. What are the things that you have to know in order to move forward? What are the essentials? There's 5. Can you identify significant digits? Can you use them in calculations? Can you make appropriate estimates and measurements? Can you do mass by difference? And can you calculate percent error? Guys, are any of those surprising to you given what we did in the last unit? Those are the big things, right? So here's what we're going to do. Guys, do this with me. Can you identify significant digits? How do you know? Guys, look at multiple choice on your bubble sheet. Look at multiple choice questions 45 through 53. There are 9 questions there. Look at the bubble sheet and not at the test. Guys, looking at the bubble sheet 45 through 53, how many did you get right? Take that number and write it right there. Do this. Count up the number that you got right. That means there's no red mark next to it. 45 through 53 and write it on the line. Now, guys, the next thing you do is you look right here. The mastery level is 7 out of 9. So if you got 7, 8, or 9 correct, you can say with confidence you have mastered that. Circle yes. If you got 6, 5, 4, 3, 2, 1, or 0 right, then you have identified a weakness in your understanding and circle no. You now know whether or not you've mastered significant digits. Now, moving down, what about using significant digits in calculations? That's multiple choice 54 through 56. How many did you get right? Write it on the line. The mastery cutoff, guys, is 2. So if you got 2 or 3 right, then yes, you have mastery. If you got 0, 1, or 2, then, 0 or 1, then no, you did not master that, and circle no. Then, guys, flip your test over to the lab. On the back, can you make estimates and measurements? That's your data chart. It was out of 6. What did you get out of 6? If that number is a 5 or a 6, circle yes, you mastered it. If that number is below 5, then no, you did not master that. Then, guys, finding mass by difference, that was worth 5. Write down the score that you got. If that number is a 4 or a 5, circle yes for mastery. If it's less, circle no. Then, guys, finally calculating percent error. Write the number that you got out of 5. If that is a 4 or a 5, then yes, you mastered it. And if it's lower, no, you did not. Yep. Let me look at it with you. Guys, we okay? That may have just been because, Kate, as I was grading it, my brain got soft and I thought it was worth 5. You know what? Here, let me do this. Guys, are you okay? Okay. So now, guys, what you need to do is zoom in literally at the bottom of this page and let me... Oh, man, I'm sorry. Yeah, that's my fault. So make that a 6. And then I'm just going to make a note to myself to add actually now 2 points to your test because of that multiple choice. Thanks for catching that. Okay, so guys, here's then what you're going to do. Test score. Find your test score and write it right here. Now, circle where that puts you. Are you below or above 85? And if you are at 85, circle the one on the right. It's 85 or above. Now, guys, do this. Look up at all the yeses and the nos that you circled. If you circled all yeses, circle yes on the left. If you circled any no's, circle no on the left. And now, guys, there's one more box that you need to check, but think through this with me. So, guys, this is the way that this goes. If you have a yes, and if you are above 85%, congratulations. You're off to a great start. You've mastered everything that you need to, and you did very well on this test. Congratulations. You're right where you need to be. Now, guys, what if you circled yes, but you were in this region? Guys, what does that mean? Do you know all the essentials? Yeah. If you circled yes, you know all the essentials. So if you know all the essentials, why did you get less than 85? You don't know the fluffy stuff, and we don't care. So here's what we're going to do. If you got all the essentials right, and if you got between 75 and 84, I'm going to give you extra credit without you doing anything. You don't have anything you need to relearn because you know all the essentials. If you got all the essentials right and you got less than 74, I'm going to raise your grade to 75 and you don't have to do anything. Make sure you're checking the right boxes. Now, guys, what if you're down here? What if you got no? What if there's something you didn't master? Well, guys, if there's something you didn't master and you got better than 85%, chances are good it's something you understand now. Guys, what if you circled no and you're down here? And guys, the answer is you are going to do remediation if you want. Guys, I can't force you to do this. If you don't care, neither do I. But guys, if it's important to you to learn this material and get credit back, guys, look at what we've done to help you. This is called the remediation process. When you do this well, you'll either get extra credit or I'll raise your test score. But guys, how does the remediation process go? Check this out. This was an amazing amount of work. This is cool. Guys, this is what remediation looks like. Go out to our website, click on our link, and then go to October. Guys, this is next week. Here's how remediation works. Again, it's optional. If you don't want to do it, that's your choice. But if you want to get on top of this stuff you don't know, here's what you do. It's Tuesday, Wednesday, and Thursday of next week. Guys, Tuesday and Wednesday is an or. It's either Tuesday or Wednesday, you choose. Thursday is for everybody. And if Thursday doesn't work for you because you've got something going on, come and talk with me. I can flex with you. But it's Tuesday or Wednesday, and then Thursday for sure. And guys, this is how this goes. So remediation goes like this. When you open up our website, this is what first comes up. And guys, this is remediation. Is before Tuesday or Wednesday. And it's completely up to you. But guys, before Tuesday or Wednesday, you are going to first of all watch a video that is 30 minutes long that covers the material that are the essentials. As you do that, you're going to take notes. Then, when you're done watching the video, you are going to download and print a homework assignment. You're going to do it, and then you're going to check your answers. At that point, you're ready to come in during Pride on Tuesday or Wednesday. Now, guys, understand, I'm not going to give you an I. I've got a letter that invites you to Pride that you will give to your third period teacher. So guys, what you'll do is you will come in with your video notes and your completed assignment. If you're missing either of those, you will not be allowed into the room. During Pride on Tuesday or Wednesday, we have a tutor session. Miss Call is in here with me. We work together to answer all of your questions. Once you're satisfied that you understand everything, we will then hand you another homework assignment. You will then complete that assignment as homework, check your answers on that, and by that point, guys, you're going to understand everything. Then on Thursday, you will bring in that completed Pride assignment, you will come into class, you will take a replacement test, and if you get better than 80% on that replacement test, which everybody does, then you either get extra credit or your score goes up based upon your original test score. Guys, this works awesome. Go ahead.
So if you get like an 83 on the test, it's possible to get less than that, get an 81 on the replacement test, and still.
Correct. But understand, if you hit 80, that's all you need. So say that's the case for you. I don't know your test score, but say you got an 83 and you're like, well, what about this? Say that you got an 83, but you got all the essentials correct. I'm going to give you extra credit without you doing anything. But if you got an 83 and missed some of the essentials, you go through the remediation process, you get better than 80% on that test over just the essentials, and I give you extra credit.
Do you give it, so let's say you take the replacement test, you get an 81. Do you give extra credit on the 81 or extra credit on the 81?
Any score better than 80% tells us that you've mastered the essentials. You've met the benchmark, you get extra credit. Is that okay? Go ahead.
And this extra credit, is that on your test?
No, so what's going to happen is it actually goes on your homework. And it actually, the way that it works out is it allows us to better control the value of the extra credit. It's a long story, and I'll explain it to you later. And guys, I don't know if you know this or not. Do you know that most of the extra credit that you get in your classes actually doesn't affect your grade? Do you understand that? That Skyward actually caps extra credit, and you can't get better than 100% in a category. And I'm the only teacher that I know of that's ever questioned this, and I've been working with the district over the last 2 years to try to fix that, and they finally got back to me and said that it's unfixable. So what I end up doing is taking that extra credit, and at the end of the quarter, I spend the time to hand calculate your grade, and then I do a grade change so that your grade actually does benefit from the extra credit, where most of your teachers don't even know the difference, and you're not getting all the extra credit that you're earning. So I'll explain it more to you later. It's kind of a weird deal. So guys, other questions? Things we need to talk about? Y'all okay? Pretty good deal, right? Don't you wish that you could do this in all of your classes? Know what you need to know, and anything you don't know you can fix for points? It's kind of a good deal. So guys, with that said, if you're sad, what I need, please, is the paper that is your evaluation paper. Please hand them to the aisles. No. Guys, evaluation papers first. Gimme. Yep. Thanks, sir. There we go. Thank you. Thank you. Thank you. Thank you. Did I get them all? Oh, wait. Here we go, Eli. There we go. All right, guys, the next thing that I need from you is your tests. If you walk out of here with these tests, you made a mistake. Because, guys, these are not public domain. So just give them to me. Hand the test to the aisle, please. Thank you. Hand them down. Here we go. Thank you. And then, guys, the last thing that I need from you are the labs that we did last time. Rummage those out of your notebook and turn in, and if it's in the basket, that's fine. Guys, I need your labs from you, please. And then, guys, so long as you've got your notebooks open, why don't you grab your periodic tables? And Laurel, where are you at? That's the wrong class. Oh. All right. I got yours. So guys, do you have these labs? Me?
Yeah.
Okay. So guys, labs, if you would, please. Thank you, Silas. Thank you, sir. Thank you, sir. Thank you, ma'am. And thank you, sir. Hey, so guys, while I'm back here, Silas, I'm going to make a mess on your table. Sorry. Did you guys get homework? You guys did? Did you guys get homework? You got those? Oh. Okay. Yep. And then you guys did not either, right? Okay. Here we go. All right. So guys, everything that we just went over that felt exhausting and long. Oh, Silas, sorry. Everything that we just went over. Guys, for the rest of the year, that takes 5 minutes. I don't have to explain it to you. You just do it on your own. I'll answer questions if you need, but it goes way faster in the future. So, guys, any questions about all that stuff that we just talked about? You okay? We're good? Okay. So, guys, you should have a packet of paper in front of you. Did you all get one? Do you get it? So guys, those are your class notes. I actually printed all of your notes for you today. So all you need is this packet of paper, and we're going to get going, and a pencil. That's it. So guys, here's what we're going to do. I'm going to set the stage today by explaining to you what we've done and how we're going to move forward. And then guys, after that, I'm going to call time out for a minute. And I need to share a thought with you. And then once we've done that, we're going to dig into some material that frankly is wacky. You're going to like this. We will work probably close to the end of the period. But guys, it's not going to feel slow or, oh my gosh, you got to be kidding. This stuff's It's cool. You'll see. So, guys, here's where we are. So, go ahead. You guys do know that that is the best pencil sharpener in the school, right? Oh, I told you. All right. It actually might. You never know. So, guys, here's where we are. Remember the triangle, right? And we've done elements, compounds, solutions, and heterogeneous mixtures. And guys, I'm just going to be honest with you. And maybe I told you, you know the lab that we did last time? Did I tell you that we've never done that lab before here at Orem High? Miss Collin, I made that up over the summer. And anytime you do something for the first time, you're a little skittish. You're like, oh, is this going to work? And guys, it worked beautifully. And a lot of that is because of you guys. You work well in lab. And thank you. But guys, it accomplished exactly what we wanted it to accomplish because it got you thinking through elements, compounds, solutions, and heterogeneous mixtures. Now guys, with that said, here's what we're going to do for the rest of the unit. We are going to focus in on atoms. And guys, when we do, we're going to answer these three questions. Read them with me. Where do they come from? How big are they? And what are they made of? Where do they come from? How big are they? And what are they made of? You get the idea? Okay, so guys, with that said, don't be offended, but hear me out. Ready? So guys, we live in Utah County. Wow. I know. Some people are. They leave. But guys, living in Utah County means that we live in a place unlike any other place on earth. Guys, it's not even like this in the Bible Belt with Southern Baptists. I don't know if you understand that. But guys, you live in a culture that does not exist even over Point of the Mountain. You live in a place that is dominated by a single religious group in a way that is not the case anywhere else on earth. Well, anywhere else in the United States. Now, guys, because that is the case, many of you are people of faith, and specifically a Judeo-Christian faith. And guys, if you don't know what that means, it means you ascribe to the Bible as being more than just a book. Now, guys, understand that that is something that we share in common. I, too, although I'm not LDS, ascribe to a Judeo-Christian faith. So, guys, why do I bring this up? And here's the answer. Guys, we are also people of science. We are in a science class. And guys, understand that for some of you, you are actually going to be moving as you move through your academic career into scientific careers. When you get to the university level, you are going to declare a major in science. And guys, here's the thing that you've got to understand. The day is coming that if you are a person of faith and if you choose to pursue a career in science, there is going to come the day when tension is going to form. There is going to come the day when you are going to be asked to choose between science and the book of Genesis. Guys, here's the thing. I went through that experience as well when I was in college. And guys, I am not going to share with you how I make sense of that. I am not going to challenge your thinking. I am not going to try to indoctrinate you with what I believe. I'm only going to warn you and encourage you. Guys, the warning comes like this. Some of you think that if you go to BYU, you are going to be protected from that place where your faith is challenged by science. And guys, I'm going to tell you right now, the most frustrating conversations as a person of faith, the most frustrating conversations that I have ever had in my life with university professors about this tension between faith and science was with biology professors at BYU. And guys, I have had biology professors at BYU tell me that if I want to be good at science, I have to check my faith at the door, because it's foolish to allow faith to inform our understanding of science. So guys, this is my encouragement. And I can't share with you anything that I believe, but this is my encouragement. When that day comes, when your faith is challenged by science, guys, do not ever let somebody tell you you have to pick. If you are a person of faith, you do not have to abandon your faith to pursue science. Guys, there is a rich and wonderful space that exists between those two extremes, and it's where I live, and it's where a lot of really, really intelligent, faithful people live. And if you have anybody get up in your face and say, if you want to do science, you have got to abandon your faith, don't listen to them. Because guys, it's simply not true. Now again, I can't share with you how I make sense of this. All I can do is encourage you. Don't let them force you to choose. You understand what I'm saying? Okay. So guys, with that said, here's what we're going to do. We are going to have a conversation about elements that starts with atomic evolution. Now guys, when you hear evolution, you think about monkeys turning into people. Guys, that is not what evolution means. Evolution simply means change over time. And I would propose to you that you can believe in evolution and still grasp a hold of the book of Genesis. So, with that said, guys, here's the deal. This ledge right here is right now. This is now. This is today. This is you and me. Okay? Now, as we move this way, this is going back in time. And guys, all the way over here by Caleb, this, do you need to go? All the way back over here, guys, this is 13 billion years ago. And guys, 13 billion years ago, something magic happened. 13 billion years ago, there was this thing that existed called the singularity. How big was the singularity? Smaller than an atom. What was inside the singularity? Our entire universe. Not the Earth, not the solar system, not the Milky Way galaxy, but guys, inside this singularity was the entire universe. And guys, 13 billion years ago, what did that thing do? Blew up. And boy, oh boy, did it blow up. What do we call it? The Big Bang. 13 years ago, this singularity blew up. And guys, when it blew up, it expanded. And as it expanded, it cooled down. And as it cooled down, it finally got cold enough that it was cool enough that protons and neutrons and electrons could exist. And when that happened, one proton and one electron, because protons are positive and electrons are negative, one proton and one electron got together and they started doing a little dance. And what atom did that make? Well, that's element number one, which is hydrogen. And as the universe cooled down, initially the universe became a big ball of hydrogen. Now, guys, what we're going to do is we're going to pick it up from there, and we're now going to answer these questions. You've already got them. Just a second. Let's just read them. It says, where did hydrogen come from? Simply put, what are stars? What are the heaviest elements stars can produce? Where did heavier elements come from? And then what is the heaviest naturally occurring element? Now, and I haven't forgot you. Guys, we're going to watch a video about this. Don't try to answer the questions during the video. We'll come back and do it in a minute. But go ahead.
Oh, I was just wondering, you said a proton and electron.
Yeah.
Where did neutrons come from?
So neutrons We have time to talk. So, protons and neutrons are made of smaller things. Do you know what they're called? They're called quarks. So protons and neutrons are made of smaller things called quarks, 3 each. But as matter started to condense into protons and electrons, neutrons were there as well. But a neutron doesn't have a charge. Therefore, it wasn't initially drawn into these atoms. So the very earliest atoms were protons with electrons moving around them. Then later, heavier elements were formed, and that's when neutrons started to get into the mix, but that didn't happen in the Big Bang. It happened later, and you're about to see where. Okay, but that's a great question. So guys, what are you looking at here on the screen? And the answer is, it is a stylized picture of our early universe, and these clouds are clouds of hydrogen. But now guys, there's something important for you to understand. Hydrogen has mass, and because it has mass, it has gravity. And because it has gravity, it pulls on other hydrogen atoms, and they started to clump together. And as they clumped together, this is what happened.
As hydrogen piles on, the central region grows more and more dense, until something brand new lights up the universe. A star.
So guys, this is the deal. These hydrogen atoms start to clump together. As they clump together, they form stars. Guys, did you know that all stars are huge, huge balls of hydrogen? Keep watching.
These first stars are hydrogen giants, 100 times or more larger than our own sun. Such massive stars are short-lived, 2 or 3 million years at the most, and they go out with a bang.
Now guys, that's not the Big Bang, that's just stars blowing up.
An explosion so big, they've been dubbed hypernovae.
Now guys, did you notice this? These original huge stars, he said that they were 100 times bigger than the sun. Why would he mention the sun in a conversation about stars? Did you guys all know that? That our sun is a star. And guys, the thing that's almost poetic about this is our sun, our star, is a very, very average star. Guys, if our star was any bigger or any smaller, we wouldn't exist. They call it cosmic fine-tuning. If you're interested, look it up. But guys, here's the thing. If our sun is a star, why does it look yellow instead of white, and why doesn't it twinkle? It's too close. But guys, understand that if there's life in other parts of the Milky Way, those aliens look back at us, and our sun looks like any other star in the heavens, and it twinkles. Guys, our sun is a very average star. And then
And
they
it's
blow
with
up.
these cataclysms that the universe begins to accumulate the building blocks of life. All the atoms in the universe heavier than hydrogen and helium are forged by stars.
Stars are really interesting. They don't just sit there. They know because they last so much longer than we do. We think
So Megan, this is the answer to your question.
they're permanent.
Stars are the ultimate alchemists. They turn light elements into heavier ones. They get the energy that they need to glow that way. The star begins its life made out of hydrogen and helium mostly, about 70% hydrogen, 28% helium in the case of the sun.
In a star's core, the temperature and pressure are so high that hydrogen atoms fuse together to make helium.
Now, guys, did you understand that? So inside our sun, what is happening is these hydrogen atoms are so hot and under so much pressure that they mush together, and when two hydrogens get together, they make helium. So our sun is slowly converting hydrogen into helium. This is what all stars do.
Hydrogen fusion releases prodigious amounts of energy, the heat and light of a star.
That's the story for 90% of the life of a star, fusing hydrogen to make helium.
Eventually, though, the star runs out of hydrogen and begins to fuse its stocks of helium, making yet heavier elements.
And so the way it works, and it always works this way, is that it contracts and it gets hotter. And if it can find something new to burn, whether it's the kitchen sink or coal or whatever, it'll burn it.
Helium is taken 3 at a time to make carbon.
You can add one more helium to that carbon and make element number 8, oxygen.
That's a tremendous step forward. You get carbon and nitrogen and oxygen made in stars.
Now this is great because on the board we already have the principal elements of life.
Organic chemistry is the chemistry of carbon.
Carbon fuses next, and still heavier elements begin to form.
Sulfur, argon, chlorine.
Potassium, calcium, scandium. The pace of this gets faster and faster.
Back in the middle, silicon is starting to burn at 3.5 billion degrees, stupendous temperature.
It makes titanium, vanadium, chromium,
Manganese, cobalt, nickel, and iron.
Iron is really the end of the road. It's sort of the nuclear turnip out of which you just cannot squeeze anymore.
It's the end of the game. A star that has relied on fusion has come to the point where it has nothing more to spin.
The star is suddenly caught in a disaster. There's radiation going out from the outside, but deep in the inside, there's no more fuel.
Iron can't fuel this stellar furnace, and so, when a star builds up too much iron, it dies.
The core collapses, it bounces,
And it begins to move out, first slowly and then faster and faster.
and that sends a very sharp wave back out through the star.
And now what was falling down is going out, the whole thing's blowing up. And you've made a supernova.
The supernova explosion can be as bright as 4 billion stars like the sun.
A stupendous explosion.
Such outrageous energies overcome the iron barrier, cooking atoms into all the rest of the elements on the periodic table.
So starting down here, you can go copper,
Zinc,
gallium,
germanium,
arsenic,
zirconium,
indium,
niobium, molybdenum, technetium,
strontium,
rhodium,
lutetium,
antimony,
ytterbium,
tellurium,
thorium,
iodine,
radon,
xenon, cesium,
francium,
barium, lanthanum,
tellurium,
cerium,
indium,
actinium,
xenon,
thorium, protactinium,
cesium.
uranium. Done. That's enough elements.
So guys, let's review. Looking at the questions and trying to answer them, here we go. And the singularity blows up, it starts to cool. The first element that it makes is hydrogen. So question number 1, where did the hydrogen come from? Big Bang. And guys, that continues to be the case. But then guys, this hydrogen starts to ball together because of gravity. They pull on each other, these hydrogen atoms clump together, and what do they make? Stars. So what is a star? It is a large ball of hydrogen. But inside that ball of hydrogen, fusion is taking place, making heavier elements. So guys, we get hydrogens fusing into helium. Helium and hydrogen makes lithium. 2 heliums make beryllium. 3 make carbon. Then we get, and it just gets heavier and heavier and heavier, and we get all these heavier elements until we get to which one? Iron. Question 3. Is it question 3? Yeah, so guys, the heaviest element that can be produced in stars is iron. And guys, that's why there's a lot of iron that exists here on Earth, because these elements then pull together and make planets, and iron is so abundant because it's the dead end in most stars. Now, at that point, guys, a star can no longer fuse things to iron to make heavier elements. The star starts to run out of fuel and it dies. But instead of going black and going away, it collapses and it bounces and blows up. And what do we call it? What is that explosion called? not hyper, supernova. The hyper were the giants blowing up. So these are called supernova. And guys, when that happens, so much energy is released that now we can actually even get iron diffused together, and that makes all the heavier elements up to which one? Uranium. Uranium, guys, is the heaviest element that exists in the universe. But now you're going, wait a minute. If that's the case, then why does my periodic table keep going? Do you know the answer? Go ahead, Silas.
Because
We make them. Yeah. Guys, here's the thing that's weird. Up until uranium, where do all of these elements exist? Everywhere. After uranium, where do these elements exist? And the answer is Moscow, Geneva, Switzerland, and California. Because Russia, the United States, and some rich nations in Europe actually support university labs that create these heavier elements. And guys, in the next unit, we're going to watch videos about how they do that. But guys, exactly, particle accelerators, atom smashers. But guys, every element heavier than uranium only exists on planet Earth because humans are here, men and women, making these elements in research laboratories. They don't exist anywhere else in the universe. Crazy, right? So guys, any questions on the questions? Y'all good? Go ahead. You know what? Can I jump on my soapbox for a minute? Guys, Cade's question is brilliant. Cade's question is, what's the purpose of making these heavier elements? And the answer to that question, frankly, changes depending on if we have a Republican or a Democratic president. It really does. Because, and again, these are platforms. Within the Democratic Party, there is a sense, as you said, that humans are curious. And because we're curious, there's value in doing research just so we can learn stuff. I think that's pretty cool. The other side of this question is, why should we do things if it doesn't make us money? Kind of a more of a Republican standpoint. And that is always going to be a tension. When Republicans are controlling our government, funding for research goes up. When Republicans are covering the government, funding tends to go down. And there isn't a right or wrong answer, because every dollar that we spend making element 115 is a dollar that we can't spend fixing our roads. Right? So we have to make a choice. And that's the fundamental question. Why do it? Because it doesn't do anything for us other than let us fill in the periodic table. And there isn't a solid other than like, for example, this plutonium. We built bombs out of that. Really amazing bombs up cities. So some of these things they do have a value, but most of them don't. Just cool to think about. Yeah. You guys good? Question number 2, y'all. Here we go. You're good on these questions? Guys, question number 2 is this, another video. Around us is made of atoms. You, me, the kitchen sink is all atoms. We now know where they come from. Big Bang, stars, and supernova. But guys, here's the question. What are they like? What is it like to be or see an atom? And the answer is we don't know. We've never seen an atom. They are so small that we can't see them, no matter how hard we try. So, how small are atoms? Well, guys, it turns out that a group proposed that question to a professor. I think he's from New York, and this is what he came up with. So here's the question. How small are atoms? I gotta be honest with you, this video gets really weird.
You probably already know that everything is made up of little...
This is actually kind of what that professor looks like. The whole thing's a cartoon.
tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are.
Is that too loud?
Well, the answer is that they are really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit?
Okay, so here's the question. Picture a grapefruit, right? It's a citrus fruit about the size of a softball. So the question is if you've got a grapefruit, how many atoms are inside the grapefruit? 300 billion and 11. No.
Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry.
Okay, so here's what we're doing. Getting a little weird, but hear this. So guys, we are now taking our grapefruit and we're grabbing each of the atoms, and with a bicycle pump, we are pumping up those atoms until they're about this big, the size of the tip of your pinky, about the size of a blueberry. So if we take every single atom inside of a grapefruit and pump them up, how big does the grapefruit get if each of the atoms is now the size of a blueberry? Actually, yes.
And then how big would the grapefruit have to be? It would have to be the same size of, well, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit? That's...
All right. So guys, here's what he's saying. Let me go back. Because guys, if you wrap your head around this, this is nuts. So ready? In order to understand this, do this in your mind's eye. Picture the Earth. Now, fill the Earth with blueberries. That's how many atoms are inside a grapefruit. Guys, imagine digging a hole in your backyard. But imagine digging a hole in your backyard that it's big enough that you just gutted the earth. And then fill that with blueberries. That is how many atoms are inside a grapefruit. Oh yeah, it gets worse. Oh yeah, just wait.
Of nitrogen atoms as a grapefruit? That's right. So how big's the atom? Well, that's really, 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 really small.
You sold on that? Does the eyeball kind of freak you out? Me too.
And you know what? It gets even more crazy.
Okay, so now guys, we have a sense of how small the atom is, but how big is the middle of the atom, which we call the nucleus?
Let's now look inside of each atom. That's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus?
Now you guys know this, right? Protons and neutrons in the middle, electrons outside.
Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house.
All right, so now our atom, which is a blueberry, is the size of a two-story house. How big then would the nucleus be?
So imagine a ball that is as tall as a two-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium.
All right, so now our blueberry, which is the atom, is the size of Lavelle Edwards Stadium. Now watch.
So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble.
All right. So guys, imagine this if you can. Imagine being, if you've ever been there, but if not, you can probably picture. Imagine being in the middle of Lavelle Edwards Stadium, and nobody's there but you. And then imagine at the 50-yard line is a marble. That marble is the nucleus of the atom. And guys, if that marble is the nucleus of the atom, where are the electrons? They are way up in the cheap seats doing this. And guys, that is what an atom looks like. The nucleus, if it's the size of a marble, the atom is the size of Lavelle Edwards Stadium, and the electrons are going out here. But guys, the rest of the stadium is completely empty.
Lots of empty space.
So are atoms. Guys, atoms have as much empty space in them as a football stadium with a marble in the middle. Now, guys, this is a problem, right? Because, guys, what are we made of? Atoms. But, guys, wait. We're solid, right? We're solid. We're not. Guys, solid is an illusion. No, because guys, the atoms that we are made of have as much empty space as a football stadium with a marble in the middle. That's how much empty space makes up us. If you could suck all the empty space out of us, our entire body would shrink down to something smaller than a grain of sand. Now, why? Hold on. Why, guys? How is it that we think we're what makes atoms solid if they're actually mostly empty space? Do y'all know? Just a second, silence. Do you guys know? Do you know? Go ahead, kid. That's it. It's the electrons moving. Guys, those electrons moving around the outside of the atom create a barrier that you can't get through, and as a result, it makes the atom appear to be big and solid, while in fact, they're mostly empty space. Go ahead. I know, right? What were you saying, Justin? Are you sure? Come on. You sure? Okay. Crazy, right? All right, guys, we got one more to go. Atoms are mostly empty space.
And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium with a nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons?
What's the answer? What's between the nucleus and the electrons? Empty space.
Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit. Okay, one more thing.
Why the gorilla?
Can even get more bizarre. Since virtually all of the mass of an atom is in the nucleus, now there is some amount of mass in the electrons, but most of it is in the nucleus. How dense is the nucleus?
So guys, this is the last question. How dense is we know the nucleus is the size of a marble on the scale of a football stadium, because all the mass is in there. So how dense is the nucleus? It's not in the notes, just one.
Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed.
Got it? Yeah, me neither.
But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet.
Better? No. How about this?
Okay, that's still kind of hard to figure. Okay, here's what I want you to do.
Here's what he
Make
wants
a
us to
box
do.
that is 1 foot by 1 foot by 1 foot.
And I did.
And let's go and grab all of the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus?
All right, so here's the question. If we had a box this size, how many cars would we have to jam in here to make the matter that is inside the box the same density as the density of the nucleus of an atom?
Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth.
So guys, that's the answer. To make the matter inside this box as dense as the nucleus of an atom, we have to jam 6.2 billion cars in here. And then it's as dense as the nucleus of an atom. Go ahead, John. Me too. I have lots, but go ahead.
When you so when you put a lot of mass inside one point,
Yeah,
it becomes a black hole.
yeah, yeah,
So like, what's the difference? Like,
yeah. It's a great question. And the answer is that it's still not as dense as a black hole.
black hole, like,
Denser. More denserist. Right.
And then
Mm-hmm.
everything in the world is that space.
And then you got it. So guys, here's where we are.
12 billion tons.
Like that. Yeah. So guys, atoms are whack, right? That's the scientific term for they're whack. But guys, just because these things are nutty doesn't mean that we can't understand things about them. So guys, this is how we're going to wrap up the day. Switch pages. And guys, what we're going to do for the rest of the day, and we are going to run 5 minutes over. Don't pack up. We are going to run into that transitional period between now and Pride. You won't hear the bell ring because I've muted stuff. I will take care of you. We're going to run for 5 extra minutes and we'll still get out on time. So, guys, grab this table and let's fill it out. This is not mind-boggling. This is not things to think deeply about. Just write it down. Guys, atoms are made of protons, neutrons, and electrons. Now, the protons and neutrons, as you know, and guys, look right here, the protons and neutrons are in the nucleus. So we call them nucleons. Now, moving from left to right, when we abbreviate protons, we abbreviate that capital P positive. And guys, the capitalization is important because it means massive. So, how massive is a proton? Don't write it down. Guys, this is the mass of a proton in grams. It looks like this when you write it out. And then you go, wait a minute, that's a really small number. Yeah, but that's a bunch of mass when you're as small as a proton. But guys, this number is ridiculous, so instead of that, we measure the mass of protons in another unit called AMUs, atomic mass units. And in those units, the mass of a proton is 1. Now, the charge of a proton, you know, is positive. But it's not just positive, it is actually positive 1. That'll be important in a minute. Now, guys, moving along. Neutrons, the abbreviation is capital N0. If you were paying attention, the capital letter means massive. How massive? The same mass, don't write it down, the same mass as a proton. So if their masses are the same, what's the mass in AMUs? 1. Then, guys, you may know that neutrons have no charge. The charge is 0. Now, guys, electrons, be careful. The abbreviation of an electron is lowercase e negative. The lowercase means not very massive. The mass of an electron, again, don't write it down, is actually about 10,000 times smaller than that of a neutron, or a proton. So, guys, electrons don't have a lot of mass, but they do have some mass, but it's so small we call it 0. But they do have charge, and that charge is -1. Now, guys, in order to move forward, there's a couple things that you need to know. First of all, notice this. Protons and neutrons are the particles that carry mass. You may want to include that in your notes. Protons and neutrons carry mass. Protons and electrons carry charge. And guys, that is important, and this is going to come up underneath the table. That is important because atoms do not have a charge. They are made of things that are charged, but they do not have a charge. What that means is the protons and electrons are equal in number. So now, guys, we're ready to figure out how many protons, neutrons, and electrons are in an atom. To do that, switch pages and grab your periodic tables. But keep your notes in front of you. Guys, in order to figure this out, there are two numbers that we need. Guys, the first number, watch my laser, the first number is the small number, the big number in blue. That number, guys, is what we call the atomic number, abbreviated Z, and it tells us the number of protons in the nucleus, if you want to get that in your notes. The other number that we need, guys, is the small number in red. That is the atomic mass, and it is the number of protons and neutrons in the nucleus. And they are not whole numbers, so we will round them to the nearest whole number and talk more later. Now, guys, we are going to skip then the rest of that slide. So when you're done with this, you're good. You okay? We're still going to be done at noon. You okay? So, guys, given this information, how do we then know how many protons, neutrons, and electrons are in an atom? Next slide. Guys, how do we know how many protons are in an atom? It's the atomic number Z. How do we know how many electrons are in an atom? It's the atomic number Z because it's the same as protons. Now, how do we know how many neutrons are in an atom? And guys, this is like a mass by difference calculation. The number of neutrons is the atomic mass minus the atomic number. Does it feel wrong that we're not doing the pledge? You can do it twice on Monday. It'll be fine. Okay. You guys okay? So, guys, we're going to do this twice, and then we're done. We got about 45 seconds left. You ready to go on? Okay, so, guys, find the circle. There it is, and it's in your notes. And guys, this circle, as your notes indicate, is going to be a potassium atom. So guys, find potassium on the periodic table, and it's right here, element 19. So guys, the atomic number of potassium is 19. What is its mass in red? 39.0 something. We're going to round it to 39. So guys, what does that mean? Well, if this is element 39, if it's element 19, 19 protons in the nucleus. Does that make sense? Now, guys, as soon as we know 19 protons, what other thing is there 19 of? Electrons zipping around the outside up in the cheap seats of the stadium. Now, guys, we need to know neutrons. So how many neutrons? Well, the mass is 39. The atomic number is 19. Subtract them, and the difference is the number of neutrons, 20. Now, guys, I have a question for you. Nucleus was the size of a marble. How big would this outer ring be? Lavelle Edwards Stadium. Okay. Guys, because these are not drawn to scale, we are not going to use them. We're going to do this. Grab your homework. Guys, this is your homework. For the sake of time, we are not going to start on number 1. We're going to start on number 2, and we're going to do it together. But guys, before we do, watch this. We have the substance, we have the abbreviation, we have Z, we have A. Now, guys, if you want to write this in, this is going to make your life a lot easier. How do we know how many protons are in an atom? Z. How do we know how many electrons are in an atom? Same as protons. How do we know how many neutrons are in an atom? A minus Z. And guys, from that, we can now fill out the table. I'd like to do number 2 with you. Guys, notice the only information that we're given is the atomic number. But that's all we need. Because element number 12 is magnesium. Guys, there is not a rule for capitalization. Magnesium. But guys, there is a rule when you abbreviate it. Big M, little g. Now we need the mass, and the mass of magnesium is 24.3. We're going to round it to 24. We're going to round them to a whole number every time. Now guys, at this point, the number of protons is the same as Z. The number of electrons is the same as protons. And you can fill out the rest of the table. Then you will flip it over onto the back, and you will notice that there are opportunities there for you. Also, the opportunity for you to think through the analogies that were given to you in the previous video. Guys, we will look these over on Tuesday, and then we'll cover